So, welcome to the Graphics Programming Virtual Meetup. Today we will continue talking about the PBRT book, where we talk about light sources, and today we will talk about distant light, and I think also next chapter area light. Okay, let's start. So another useful light source type is a distant light, also known as directional light. Describes the emitter that disposes illumination from the same direction at every point in the space. It's also called the light point at infinity, since as the point light becomes progressively farther away, it acts more and more like directional light. For example, the sun. Although it's actually an area light source, it's effectively arrived on Earth in nearly parallel beams. Distant light construction does not take the medium interface parameter. The only reasonable medium for a distant light to be is in the vacuum. If it was itself in a media that absorbed any light at all, then all of its emission would be absorbed. Since its model as being infinitely far away. So it takes a transform, a spectrum, and scale. Those two just decide the spectrum of the emitted light and transform. Some of the distant light method need to know the bounds of the scene. Because PBRT creates lights before the scene geometry, these bounds are not available when the distant light constructor executed. Therefore, distant light implements an optional preprocess method where it converts the scene bounds to a bounding sphere and it should be the representation to work with in the following. Oh, okay. Okay, it's alt parameter. So they create a bounding sphere and then put them into those two. Incident radius at point P due to distant light can be described using the direct delta distribution. So the incident radius is omega and minus omega I light direction. It needs to be exactly at the light direction. Given this definition, the implementation of sample LI method is straightforward. The incident direction and radius are always the same. The only interesting bit is the initialization of the interaction that provides the second point for the future shadow ray. It is set along the distant light incident direction at a distance of twice of the radius of the same bounding sphere. So guarantee that the second point is also side of the same bond.
It's an interesting way to do that.
Yeah, it just like guaranteed it will hit something if anything in the thing. I guess. Okay, simple line. But okay, they just transform this to proper light direction, and then in the render space, and then uh, yeah, that's what they did with this, and I think this PDF is always just one, if I remember correctly. Yeah, it's PDF. Because like point light, this is a pretty special case. And yeah, this light is different than the light we have seen so far in that the amount of power it emits is related to the spatial extent of the scene. In fact, it is proportional to the area of the scene receiving lights. Yeah. Uh, Consider a disk of area A being illuminated by a distant light with emitted radiance L, where the incident light arrives along the disk in normal direction. The total power reaching the disk is phi is equal to A of L. Yeah, the area is larger, we receive just more power basically. To find the immediate power of this light, it's impractical to compute the total surface area of the object that's visible to the light. Instead, we just approximate with the scene's Bounding sphere. This will always overestimate the actual area, but sufficient for the need of code elsewhere. I think they just use this for importance sampling, so yeah, it's fine if the estimation is not accurate. And there's a code.
Yeah, depending on how densely that sphere is populated, that could be a very large overestimate.
Yeah.
That's interesting.
Yeah, just consider you have two small objects like very further apart, then it would be a very significant overestimation, but yeah. So area lights. Area lights are defined by a combination of the shape and the direction distribution of radiance at each point of the surface. In general, computing radiometric quantities related to area light requires computing integrals of the surface of the light that often cannot be computed in closed form, though they are well suited to Monte Carlo integration. The reward for this complexity is soft shadows and more realistic lighting effects rather than the hard shadows and the stark lighting that come from point light. Yeah, it's I guess it's the same area light with same power but different size, and yeah, we can see the effect drastically different. Diffuse area light class define an area light where emission at each point on the surface have a uniform directional distribution. Its constructor, if an alpha texture has been associated with the shape to cut away part of the surface, is used here to so that no illumination from those parts of the shape. And the area of emissive shape is needed in a number of following methods, so it's cached in a member variable. So we get shape, we get alpha, also an area to cache. A number of parameters specify emission from diffuse area lights. By default, emission is only on one side of the surface, whereas normal is outward facing. A scaling transform that flips the normal or the reverse orientation direction in the same description file can be used to cause emission to be on the other side. If two-sided is true, then emission is on both sides. Emission that vary over surface can be defined using an image. If one is provided to the constructor, the surface will have spatially varying emission defined by its color values. Otherwise, spatially uniform emission spectral radiance is given by a provided L-image spectrum. Also, additional scaling factor. Okay, so basically we have two scaling factors. One is the float, another is the image. On top of this, I think. Recalling from section 12.1 that light interface include the L method. That area lights must implement to provide the emitted radiance at a specific point on their surface. This method is called if they happen to intersect an emissive surface. For example, diffuse area light implementation start by checking a few cases in which there are no emitted radiance before calculating emission using image, if provided, otherwise just constant. So first check if zero emission, otherwise calculate the radiance. So two cases allow immediately return no emitted radiance. The first is if the light is one-sided and outgoing direction face away from surface normal. Yeah, simple case. Also, if there is a alpha mask. The alpha mask method performs a stochastic alpha test for a point. Okay, it's just a fancy way to say if alpha is between 0 and 1, we do some random. Yeah, okay. If an image has been provided to specify emission, then the emitted radiance is found by looking up an RGB value and convert to the requested spectrum samples. Note that the V coordinate is inverted before being passed to bilerp channel. In this way, the parameter addition matches the image texture coordinate convention that described in previously. Okay. Oh, so if there was image, they completely don't use this, it seems. Okay. So they just either use image or this, depending on whether they have an image or not.
Yeah, I think the image has to be converted to a spectrum.
Yeah.
Yeah. That makes sense, yeah. Well, point sample, the image has to be.
For convenience, add a method to the surface interaction class and make it easy to compute the immediate radiance at the surface point intersect with the ray. Yeah, if it's area light, then using calling this. Otherwise, yeah, otherwise it's just 0. All the sample LM methods so far have been deterministic because all the preceding light model have been defined in terms of delta distribution of either position or direction. There has always been a single incident direction along which illumination arrive at any point. No longer the case with error lights, and we will finally make use of the sample. So the first sample point on the shape for diffuse area light, and then check sample point on shade against alpha texture, and then return the sample on the sample point. Second variant of shape sample which takes receiving point and return a point on the shape and the PDF expressed with respect to solar angle at the receiving point is exact match for the light sample LI interface. So the information start by calling this method. The astute reader will note that if an image is being used to define the light's emission, leaving the sampling task to the shape alone may not be ideal. Oh yes, because image may not be uniform. But
Right, yeah, the mask might, you might be sampling stuff that's outside the mask.
Yeah. Extending the shape sampling interface to optionally take reference to an image or some other representation of spatial varying emission would be clunky addition. So PBRT's solution to this problem is that bilinear patch shapes, but no others, allow specifying an image to use for sampling. Having this information twice in the same description is not ideal, but it suffices to make the common case of virtual literal emitter with the image work out. Okay. So for sampling points on shape for diffuse area light, we basically just sample the shape sample the shape, and then if the sample does not exist, it has 0 PDF. Or if the I think if the sample point is the same as the intersection point, then return nothing.
Is it saying that it's not illuminating itself? Or?
Yeah, I think so. If a sample point has been masked by the architecture, invalid sample is returned. Yeah, it's same. And if the shape has been generated valid sample, then the next step is compute the emitted radiance at the sample point. If that is a zero valued spectrum, then an onset sample value is returned. Calling code can then avoid the expense of creating unnecessary shadow ray. Okay, yeah. The PDF for sampling a given direction from a receiving light is also easily handled, again thanks to the shape providing a corresponding method. Yeah, just also again delegate, just like this, all the emitted power from an area light with uniform emitted radiance over surface can be computed in closed form. From equation 4.1, it follows that it is pi times the surface area times the emitted radiance.
It's kind of like having a distribution of point lights over that uniform surface.
Yeah. I think they just did the integral and if the uniform, we get that. If the image has been specified for the emission, the average value is computed in a fragment that is not included here. The current computation neglects the effect of any architecture and effectively assume that there is no distortion in the UV parameterization Otherwise, there will be error in the file value. But again, it's also okay because, like in last case, this is just estimation. So just it's fine if it's not accurate.
These like total power quantities are probably something further into importance sampling.
Yeah,
I'm not
yeah,
exactly
exactly.
sure.
For light sampling, like which light you to choose from.
Right, right.
So this is a simple case. For image, they do some more complicated stuff. But yeah. Okay.